industries. Before I start, could I ask you to save any questions for the end? Thank you. So to start, I'm going to talk a little bit about my background and career path. I haven't always worked in film. I've spent most of my career working in games. So I grew up making games on the Spectrum and then later the Commodore Amiga. In terms of a career path, I took the long way around. So spent about 8 years in higher education, getting a computer science degree, then starting but not finishing a PhD. At some point, I just decided to go for it and applied to loads of companies and finally started in Blitz Games in 2001. Over the years, I've worked for quite a few companies, many of them based in Brighton here, so you can see there's quite a few Brighton companies here. And even during the iPhone app boom around 2010, I started my own company trying to cash in on that. However, I failed to become an overnight millionaire. That's why I'm still here. I've worked on many games using lots of different engines and technologies. I hadn't considered working on anything else until I found a job listing from Framestore. They were looking for people with Unreal experience to use real-time engines in a groundbreaking way. So that sparked my curiosity. But at that point, I wasn't sure if my skill set would be transferable. I wasn't sure what the day-to-day work would be, and I wasn't sure if I could function in a world outside of games. But I was looking for a new challenge, so I took the chance. At that time, I didn't know anything about Framestore, and I'm guessing that probably very few people here would have heard of Framestore before, so I'm going to go into a little bit of history of Framestore. They were founded in 1986. They don't sell spectacles or glasses or any kind of windows. I've had to explain that quite a few times before. The company has 4 divisions. Film, which creates visual effects for movies. Episodic, which does TV content, things like The Last of Us or Foundation. Immersive, which is anything to do with virtual, augmented, or mixed realities or theme parks. And finally, advertising. Here's a small handful of the projects Framestore have worked on across these divisions. Some highlights include Blade Runner 2049, which won an Oscar for visual effects. Sorry. I clicked too soon. Top Gun Maverick, which was nominated for a Best Visual VFX Oscar. And of course, there was that moment when Paddington met the Queen at the top. As a company, Framestore have always pushed the boundaries of technology to advance creativity and artistry in their projects. For example, in the 80s, Framestore were pioneers in digitally painting on film. So Take On Me was one of the first projects. In the 90s, they brought Jurassic Park render tech to TV for the series Walking with Dinosaurs. Framestore are known for their ability to create lifelike furry creatures on screen. So starting with the Golden Compass, which you see here, for which they won their first Oscar. Since then, they've worked on everything from Paddington Bear to Rocket Raccoon. And finally, Gravity, where Framestore pioneered the use of LED light boxes to realistically light the actors. And they also won an Oscar for that. So that short history was to show that Framestore is a creative company that deploys and advances the latest technology in filmmaking as an aid to the artistic process. But what has that got to do with how the film and game industries are coming together, you might ask? Well, it's the technology that are bringing these industries together. We'll be looking at the changes that have happened in the last 10 years in the film industry and looking to the future, what further advances might there be on the horizon. Here's a brief overview of the rest of the talk. First, a quick tour of some VFX industry terms and differences from games, a little bit of background, followed by a look at how real-time engines are currently used in film. Then moving to the near future with a look at Fuse, which is Framestore's Unreal Shot engine, which was used to render the short film Flite, which we'll have a sneak peek at later. And to finish, I'll be speculating about the future of our industries. So first off, jumping back into my journey from games to VFX, a big part of that was learning the workflows, pipelines, and language of VFX. With that in mind, we're going to do a quick tour of the VFX industry. Starting with a high-level view of the stages in making a film. So it's roughly split into 3 parts: pre-production, production, and post-production. It's worth noting that each of these stages are traditionally separate. For example, assets created in pre-production wouldn't be reused in post-production. Even if you needed the exact same asset in both stages, it would be remade. We'll get into more detail about how the real-time engines have changed this later. For now, we're going to move on to other aspects of film production which are different from games. So we're going to look at asset management, rendering, compositing, and something called final pixels. So starting with asset management. In film, like in games, we create a lot of assets which need to be version controlled. However, in VFX, those assets can have different representations depending on where they're used in the pipeline. So for example, an asset could have a render representation, which we use for final renders, and a proxy representation, which would be used when animating. In VFX, it's also beneficial for the asset management system to support selective syncing. So instead of downloading the whole depot when working on a shot, you would only sync the assets required. Unreal 5 actually has a beta feature called Virtual Assets, which is quite similar to that. Because of these requirements, VFX houses tend to have their own asset management system. Framestore is called FAssetDB. So what are the differences when rendering in the VFX world? VFX rendering is CPU orientated, which means that for the most part, everything is rendered on a CPU. There's some exceptions for some applications for the GPU in VFX render pipelines, but their use is limited due to the cost of scaling GPU render farm nodes. Render farms are run on the Linux OS operating system, as it's cheap and reliable. Determinism is crucial. Why is that? Well, so each frame of a shot can be farmed out to different machines. This allows the shot containing hundreds of frames to be rendered in less time. Because of that, it's vital that these frames are always rendered to the exact same pixel values, no matter what hardware is used to render. And finally, frames can take days to render, even though a typical render farm has tens of thousands of CPUs. Next, we'll look at compositing. This animation shows how a frame is composited together from multiple layers. And coincidentally, this frame is taken from the short film Flite, which we'll be taking a look at later. This is Stevie on her airboard. We'll be seeing more of her throughout the presentation. Compositing is the final stage in the VFX pipeline. Here, all the elements of a shot, from film plates shot on set to CG models and rendered VFX, are combined and manipulated to produce final pixels. Final pixels is the term for the final output image from the VFX process, the pixels that you see up on the big screen. This is usually done in special compositing software such as Nuke, After Effects, or Flame. In film, there's a widely used term, we'll fix it in post, meaning that rather than delaying the earlier stages of production, you should as quickly as possible and correct any problems during post-production, that usually means at the compositing stage. Comp artists can fix many issues given the time and the data. On that note, we're going to look at some important data input for compositors, starting with crypto mats. Mats in general are images that can be used to mask out part of a scene. This is the splash screen from Blender. As you can see, there are many objects. Each of the objects overlap something else, and some of them are out of focus and blurred. When comping, you might want to separate this render into layers. To do that for this image, we would have to identify which pixels belong to which objects. For blurred or transparent objects, we'd also need to know how much each object contributes to the final color of the pixel. So that's where cryptomats come in. This is a cryptomat for the previous image. Multiple object IDs and coverage values are encoded for each pixel. This means that for a transparent or blurred pixel, it's possible to determine how much the object contributes to the final color. This is also somewhat related to rotoscoping, which is creating a matte from a live action still, so that an element of that still can be extracted for use somewhere else. In this example, Framestore extracted Buddy the Elf and placed him in Asda for their Christmas campaign. So that's the end of a very quick tour of the VFX industry. In the next section, we're going to explore how real-time engines are currently used in film production. By the end, we should have a better understanding of why the use of real-time engines in film has taken off. These are the main areas we're going to cover in this section. and we're going to start with virtual production. So virtual production is an umbrella term for a wide range of computer-aided production methods, combining virtual reality with CGI and game engine technologies. Together, they enable production crews to see their scenes unfold as they're captured on set. So let's start with the first of these techniques, probably the one you're most familiar with, which is in-camera VFX, or ICVFX. This technique was famously used by the Mandalorian TV series. A real-time engine is used to render to huge LED walls, like in this production shot from 1899. Because the screens are so large, multiple synced instances of the engine are used for rendering. Previously, these scenes would have been shot against green screens, and the backgrounds would have been comped in later. Using LED volumes means now that this is done now in camera at the time of shooting, hence the name In-Camera VFX. You can easily move the background around, meaning that your physical sets, actors, and cameras, and any additional lights can stay in place as you film. So you can still virtually move your shot to a new location. As it's a real-time engine, the backdrop can be edited on set. So if you don't like the look of a rock in your shot, then in seconds you can relight it, resize it, move it, or delete it. As a fallback, you can still shoot against a green screen projected onto the wall from any camera viewpoint. This allows you to have the perfect background for rotoscoping, but the rest of the volume is still lighting your scene. You can see the environment lighting coming from the wall and the tank of the bike in this shot. Just about. So all this saves time and money, as you can see how a shot will look on set, and fix it on the day of shooting rather than months down the line in reshoots. Next, we're going to take a quick look at virtual scouting. So virtual scouting presents a completely digital version of a location or a proposed set for which crew members can interact. The interaction might take place in virtual reality, on a tablet, or even on set as part of an LED volume shoot. Scouting enables filmmakers to figure out what's important in their scene ahead of filming. It can also be used to experiment and to try different ways to shoot a scene. As in this example, where the cameraman is testing out a shot against pre-captured animation. This was taken during a previous shoot for The Last of Us. Performance capture is an area in which virtual production has augmented an already well-defined process. With real-time engines, you can now visualize the motion capture data in real time, using environments, models, and lighting that reflect the final use case for the animation. Here you can see in this capture session, again from The Last of Us, that the actors' actions are mapped to the 3D models in real time. And recently, Unreal's MetaHuman animator has made further advances in terms of near real-time facial capture and realism. This example here is part of the animation short Blue Dot by Epic's 3 Lateral Studio. Next, we're going to look at the many stages of visualization that real-time engines have enhanced, starting with a quick introduction to each of these stages. And at the end, we're going to look at some of the benefits that real-time has brought to these areas. Starting with previs. So previs uses 3D imagery to visualize or design a show without incurring the high costs of actual production. You can see here that the previs that Framestore created for The Last of Us, which helped inform the final cut. As you can see, it's quite close to the final pixels version from the TV show. Closely related is pitchviz, which can help an in-development project get a green light from a studio. TechViz is the process of planning complex shots in a virtual world that simulates a real-world environment. TechViz is more concerned with physics and camera simulation than visual fidelity. For example, in this shot from Gravity, it required setting up the camera and lighting rigs on a small set, where each of these rigs was mounted on robotic arms. So to plan the shot, the set was mapped out virtually so that the movements of the camera, the lights, and the actor rig could be tested. This meant that they could be confident that the shot was going to work as planned before getting on set and having to deal with any issues there. Closely linked to TechViz is StuntViz. StuntViz is a type of TechViz used to plan stunt work. So this sequence is from Mad Max Fury Road. It was retroactively created by Gary Guy Norris to showcase the technology, but it shows how stunt viz can be used to give the director a close approximation of how a fast-paced stunt sequence will look. Lastly, we come to post-viz. Post-viz provides the director and editor more visually developed scenes to guide their work before the VFX process begins. It functions as a visual communication tool for the director to communicate with the VFX team. Some of the benefits that real-time engines have brought to the filmmaking process are: it encourages a collaborative, iterative, and non-linear production process, allowing more creativity during the earlier stages of production. The output imagery from these stages is far closer to final quality. It's possible to edit shots and sequences featuring visual effects while shooting, so the editor can work during principal photography and the crew can immediately shoot pickups. Virtual production can shift the entire crew's mindset from a fix-it in post to a fix-it in production, which allows decisions to be made earlier, increasing efficiency. All these efficiencies and increased image quality can bring benefits to more modest productions. Because of real-time engine use, network series, streaming productions, and indie films can now achieve high-quality imagery on par with blockbusters. Next, we're going to move on to something a bit more exciting and mysterious, the future of real-time use in VFX. First, to look at where real-time engines are currently used in film production. This image is from the Unreal Guide to Virtual Production. You can see that Unreal Engine is currently used right through the pre-production stage and into production, covering all the different visualization stages that we discussed earlier. However, the VFX stage in post-production is currently still the realm of offline renderers, things like Arnold and RenderMan. Integrating Unreal into this stage of production hasn't been attempted at the scale or quality that is needed to render the thousands of shots required for a blockbuster movie. Framestore, seeing the huge benefits that real-time engines brought to the rest of the pipeline, decided to invest in integrating Unreal into that final stage. That project was called Fuse, which stands for Framestore's Unreal Shot Engine. It was created to fuse together a traditional VFX shot pipeline with a real-time pipeline. Modern visual effects pipelines are designed to support huge teams of specialist artists working on a large number of complex shots, while maintaining a consistently high quality of visual output. Because of this, they tend to favor robust repeatability and granular creative control in their pipelines. Real-time engines, on the other hand, excel at rapid iteration cycles, providing a more holistic view of a shared project and scope for interactive collaboration. However, they're not designed to work with the full range of VFX departments, to fit into a live-action compositing workflow, or to deliver consistent, repeated results. The primary challenge faced in the design of Fuse was to bridge the gap between both approaches and play to their strengths. A number of key requirements were formulated for this new pipeline. It had to integrate seamlessly into the VFX pipeline tools and review processes. It must allow traditional VFX artists from multiple departments to be productive without the need for extensive retraining. It has to provide concurrent asset version access in order to allow instant comparison of different asset shot versions. It should support multipass rendering in a way that allows compositors to integrate CG from engine with live action footage. And finally, it must enable robust, repeatable rendering. I think this looks slightly different on this laptop. Sorry about that. Those requirements drove the design of the Fuse architecture, which we see here. The first section is part of the existing pipeline. So Framestore has many asset publishers that allow artists to publish and quality control their work in a fully trackable manner. For Fuse, we adapted all these publishers to work in Windows and output data compatible with the needs of Unreal Engine. The data is automatically synced to Unreal via Perforce using our TeamCity infrastructure, and the correlation between assets in Unreal and their counterparts in FAssetDB is always maintained. The creation of managed versions of these assets in Unreal is also automated, making the process of publishing an asset and being able to utilize it in Unreal transparent to the artists. We'll go through some of the other Unreal changes that you can see here later. Remote renders from Unreal can be done through a deadline managed render farm. The render artifacts can now be published back into FAssetDB, which means that they're available for the compositing team who can work on them as they did in the standard pipeline. Now look at the changes to Unreal Engine that we had to make to create views, starting with the managed asset system. At the core of Fuse is a newly implemented managed asset system designed to augment Unreal Engine's content management systems. It's designed to make large-scale version-driven linear content projects easier to work with. The key features are concurrent versions of assets and shots can be accessed locally allowing rapid iteration. Related versions can easily be swapped out depending on the usage context, providing the flexibility of having high-end VFX assets as well as real-time representations. There'll be some more on that later. And it's compatible with unmodified versions of Unreal Engine for sharing with vendors that don't have access to Fuse. For each asset, we have an asset tracker component which allows you to select the definition, variant, representation, and version that you want. So a definition is an item in a set, for example, the edge, corner, or center of a set of flooring tiles. A variant is some visually distinct rendition of the content, for example, a wet or burned rendition of a wood material. A representation is a rendition that is optimized for a specific use case. For example, you could have a high fidelity representation to be used for final renders, or a real-time representation that would be used for in-camera VFX. And finally, the version is an iterative revision of an asset. The asset management system also extends to shot-related assets. So this is managed through a custom managed sub-level editor that you can see here. In this example, the managed sub-level editor shows all the sub-levels for the shot to the left. And as with any other managed asset, it allows the users to swap out the definition, variant, and representation or version of any asset. This is an example of swapping out a managed sub-level for a different version. Here we're swapping out the Stevie Anim version for the LED wall definition. The next set of changes to Unreal Engine are to do with rendering. So for games, we need to render a frame in at most 33 milliseconds. To do that means making trade-offs to achieve the performance. These optimizations mean that the real-time render is non-deterministic. For visual effects, determinism means that the rendered pixel binary value will be exactly the same, no matter how many times you run the render on different hardware from the same input data. To account for this, during rendering, we had to turn off everything that would add noise to the renders. So paradoxically, that meant denoisers and also any other techniques that relied on randomness. This also meant we could only do sequential renders, so no splitting up jobs by frame. Compositing also had some unique requirements that we had to support. As we've seen, the role of the compositor is to bring together all the work from the previous production stages and create the final pixels on screen, like in this shot from Doctor Strange and the Multiverse of Madness. To do this, the new pipeline would have to produce the render output data that the compositing department expected. So compositors need to be able to to separate a scene into render layers. They also need to be able to render arbitrary output variables, AOVs, for each of these render layers. We're going to go over both of these now, starting with render layers. So a render layer is a group of objects in your scene that you want to be rendered together onto a 2D image, a layer. So for each layer, only the objects selected to be in that layer should be visible, but the contribution to the scene from the other object should still be there. So for example, in the background layer here, you can see that the contribution from the objects layer is still visible, even though the objects aren't. You can see the object's reflection. Oh, no, you can't. Can't see that. There are the objects, you can just about see it, but yeah, the objects that were there are still reflected in the background wall, and you can still see the bounce light and what else? The shadows. You can see the shadows, I think, in the bottom. Unreal provides stencil layers for this purpose, but as we'll see, they don't provide the clean layers that a comp artist needs to do the work. So this is the output from Unreal's stencil layer system. You can see that it masks out the objects that aren't in the layer. These masked areas cause issues in the compositing stage. For example, if we were using the layers as data for a depth of field effect, it would sample into the masked area and create a halo around the object in the final comp. Another issue here is that the stencil layers make use of Unreal's layer system to select the objects. These layers are stored within the sublevels, which isn't compatible with our managed sublevel system. So sublevels are constantly being swapped throughout the lifetime of a shot. So to overcome these issues, we implemented our own render layer system. We needed a reliable way to define which actors were defined in each layer. So to achieve this, we developed a language which would allow us to select actors based on a wildcard string match on some set of the actor properties. As part of the setup for the shot, the artist would organize the data into sublevels. So because of that, in this example, we can easily isolate the main character Stevie and her airboard into their own render layer. Once set up, these render layers can easily be reused between shots and even on different projects. To view the render layers, we built a custom browser to allow viewing in the editor. This was vital so that we didn't have to kick off a render to validate all the right objects were being assigned to each layer. We'll come back to render layers later when we talk about rendering out of Unreal. But before that, let's look at the other requirement for the compositors, which is arbitrary output variables, which are basically render passes. In this example, we have scene depth, world normals, and cryptomats, which we saw earlier. Unreal can create each of these for you as an output from the movie render queue. Note that each render layer can have its own set of AOVs, depending on what was required by the compositor for a given shot. Next, we'll look at how we render a scene from Engine. So shots are rendered through the movie render queue in Unreal. We've added a custom fuse render and other settings here to allow control over the rendering process. So things like selecting and rendering multiple render layers per job, or deciding if the render artifacts should be published back into FAssetDB. During development, we found that the artists would frequently have to set off a bunch of renders overnight. A major pain point for them was ensuring that the settings were correct for each shot. Sometimes they'd kick off a render and only find out the next day that there was a setup issue. So we added a custom UI view which allowed the artist to see and edit the setup for all the shots in the queue at once. This is a custom view of the information available in the standard editor, but organized for viewing multiple jobs at once. You can move back and forth between the views as required for your workflow. It's also possible to multi-edit the data across rows, allowing you to change settings for multiple jobs at once. This greatly reduced the errors when working on a large queue of renders and made editing multiple jobs much simpler. Another movie render queue customization was to modify the remote render functionality to kick off a build using Deadline, which is Amazon's render farm management software. It allowed us to manage and control our own render farm of Windows PCs. And it allowed us to make optimizations such as using render manifests, which I'll talk about now. So rather than syncing the whole depot to a node when rendering on a render farm, it's more efficient to only sync what's needed for the shot you're rendering. So we utilized Unreal's dependency system to create an asset manifest for each shot that we submit. The asset location and revision number would be saved along with any of the relevant render settings. This also had the benefit that we could re-render any given shot from its manifest file and recreate it exactly at any point in the future. In this example, you can see the same shot was rendered months apart while producing the same results. So finally, an important part of any production is the review process. And for that, we needed to add note-taking to Unreal. Shots are consistently reviewed and annotated with feedback for artists. The traditional VFX pipeline had its own implementation, but nothing like this existed in Unreal. So we created a plugin that allowed us to write notes and annotate scenes, which an artist could then access and review. So that was Fuse, our Unreal-based VFX pipeline. To aid in its development, Framestore also created a short film that would be used to test Fuse Fuse's capabilities on a working project. That project was called Flite. Flite is the directorial debut of Framestore's Chief Creative Officer, Tim Weber, an Oscar-winning VFX supervisor. It's an experimental short created to put Fuse to the test. It's a mix of live action and CG. For the characters, it's used our in-house machine learning skin deformation tool, Fira. Live action was captured on set using an LED volume. Some of the more complex live action shots were planned using the TechViz tools that we developed in Engine. And finally, our compositors brought all this together as they would for any other film. So the film itself is a futuristic short set in the semi-submerged London of 2053 and explores the underground practice of memory visualization. Presented as a memory, Flite forgoes photorealistic effects to capture a hyper-real quality with long, continuous, and complex shots. Here's the trailer.
Start somewhere calm, moment by moment, and we're in. When did this happen?
It was a few hours ago.
I'll get you into a memory flow. It's too fragmented. It's a prototype and it's not always pleasant.
Because I saw something. Please, you've got to help me. She might still be alive. I can't remember.
So Flite is currently being screened at festivals around the world and has already won several awards. Flite has proven that Fuse is fully integrated with the VFX pipeline. So the current asset creators can create content and the compositors can work directly with the rendered output. Flite allowed us to stress test this new pipeline with confidence that it can scale now to hundreds of shots. But more work is required in certain key areas, such as rendering. But it's clear that real-time engines can play an increasingly important role in the future of VFX film production. So this last section is about the future of our industries. We've seen that the real-time engines have been used in the VFX industry now for most of the last decade. For the most part, their use has been localized to certain stages of production. With the takeoff in streaming services and the resulting uplift in demand for high-quality VFX, filmmakers have been increasingly asking to use the real-time engines for their creative and decision-making benefits that they bring. With Fuse, we've pushed what's possible with real-time engine in a VFX pipeline even further. In the near future, we imagine that a full-length feature film will be made using this technology, and that will raise some interesting challenges. So things like training artists in the use of real-time engines and workflows. Supporting these projects will require teams of engineers, as each project tends to have custom requirements and support needs. And developing these pipelines further will require experienced Unreal engineers. As a whole, the VFX industry doesn't have the in-house teams required to spin up these projects on demand. Which brings us to what I think could be an interesting future for both industries. In my last decade in games, I was part of a growing community of work for hire studios. So these smaller studios would be brought on to help with larger projects, integrating with the development teams and working on projects as a satellite studio. This provides risk management for the larger studio. They can hire resources as needed to expand during a game's development, and then they can scale back post-development. For a smaller studio, it provides many sources of constant and diverse work. So it seems natural that in a future where real-time engines are being used to create films, we could also utilize these same work for higher resources, spreading the risk for such projects and providing a more diverse and interesting working landscape for the smaller studios. So at the start of this talk, I asked the question, why is a VFX company at a games conference? Well, much like in Moonfall here, our worlds are colliding. We're the same type of people, so creative, ambitious, and technology literate. Our industries have been separated by technology in the past, but as we've seen, that's all changed. My personal experience has been that the industries are more similar now than they've ever been before. I look forward to a future where we can all work together. So lastly, we're hiring. Talk to us at our expo booth. So today I've presented the work of many others here. So thanks go to the Fuse team and everyone who worked to create Flite. And let's see, I think we've got some time for questions. So yeah, if you've got any questions, I'll be happy to answer them.
Hi. You mentioned right at the beginning that Framestore does immersive real-time work as well. And I was wondering how, if any of these real-time techniques were being used in immersive work as well.
Yeah, we have a separate immersive division. So yeah, I think that's one of the things we're working in the future is to try to bring all these technologies together under one kind of banner. I think in the past we've had like separate divisions with different people working on real-time engines in different parts of the business. So I think that's something that we're definitely working on and trying to, is going to bring more efficiency across the company. So yeah, I think it's definitely something we're thinking of doing, yeah.
Thank you.
Okay. Why did you choose Unreal, and did you consider any other choices?
Actually, I wasn't on the project at the start, so I don't know if I can answer that. But I think across the company, in the immersive division, we've had some experience there in that division with Unreal, so that was probably the starting point. We also use Unity as well, but I think there was just yeah. From what I understand, it was just maybe the position we were in at the start of the project. Yeah. Okay.
Hi. Great talk, by the way. Thank you very much.
Thank you.
So you mentioned that with this project, you faced you realized that you had to do some more work in terms of rendering.
Yeah.
Are you able to kind of say what sort of issues you encountered?
Yeah, maybe. So I guess this project's been going for quite a few years. So we started in Unreal 4.2 and that kind of setup. So because of that, we used deferred rendering and ray tracing because the path tracer, for example, wasn't as fully featured as we needed. So, but I think with 5.2 and well, 5 and beyond, Unreal or Epic have been trying to fix up the path tracer to become more fully featured. So that would be one thing. Yeah, because the path tracer is just going to give you better quality images. So yeah, that was probably the main kind of area. Or yeah, that's probably it. Yeah, sorry.
Thank you.
Okay.
Hi, thanks, Will. Good talk.
Cheers.
You mentioned the fusion of the industries means it's like shared skill sets basically and shared tools. But do you think it can go as far as shared assets? So, given that Flite's now being built to be rendered in real time, is Flite the interactive game around the corner, or are the assets too different?
I guess in a VFX, we still have a VFX kind of company mindset in terms of asset creation. So in games, I guess you've got more time to like optimize the assets and use a continual optimization process. So in VFX, it's much shorter timeline. So you kind of make the assets as big as they need to be. Use massive assets basically. So that side of things, I think that's something we need to work on just to make sure that these projects can run on a render farm. So we were running into memory issues rendering these shots, even on like, I can't remember how much GPU memory they had, but it was like in the order of like 40 or 50 gig So yeah, we were still running into memory issues on that. So we need to get better at that side of things as well, I think, if we're going down this path. So yeah, I think, and Unreal's pushing the kind of the whole nanite kind of side of things, where we can start to reuse the same assets between industries. So I think it will depend on the projects, but yeah, I think we can reuse assets between them. Yeah.
Hello. How often are you updating Unreal?
Unreal. So I guess this project is finished. We're now doing this kind of promotional tour with it. So in terms of this project, we don't update it that often. That will depend on what's coming in the future, I guess. But yeah, other than that, we do other work in terms of the virtual production side of things. So we're kind of continually assessing. Like I think at the minute we're working on 5.2, maybe the latest revision. I'm not quite sure, but yeah, we try and keep as. And it depends on the project as well. Like once you start a project, you don't really want to be jumping to a new engine. So we support as many engines as we need to, depending on the projects we have going at any given point. Does that make sense? Okay. If there's no more questions, thank you very much for your time.